To demonstrate how we can create Microsoft Analysis Services analytic models, particularly tabular cubes, we're going to start by building a brand new data mashup in Pyramid using the Model Pro interface. For the demonstration, we're going to use two different data sources. The first is a simple Postgres database with some tables in it, and we'll accompany that with an Excel spreadsheet that we're going to upload. And from there, we're going to pull two worksheets out of that workbook. Before we continue, let's take a quick look at the data table. You can see we've got a date key column there. Analyzing that, it looks rather reasonable, but we'd like to add some time intelligence logic to that, so we just add a node like that. And we'd also like to bring in a little bit of machine learning. This is curated citizen data scientist type k-means clustering using the Weka library. And we're just going to build a quick 5-way cluster using quantity, price, and net profit. Last but not least, we're going to mash this all up to a new SQL Server relational database, which we will call SAS Demo, connect all the lines and the dots, so to speak, and get ready to build our data model. Next, we're going to go into the data model just to check the way the actual scheme is designed. And here we elect to build an MS tabular model on one of the tabular servers available here in Pyramid. Next, we're going to look at the tabular schema that is behind the model. This includes being able to use this interface to check which columns will be visible, the structure of measures, the type of aggregations. In this case, we're going to change average margin to average and also change its format to percent. And let's do one more. We'll change cost also to an average since it's average cost, and set that to a nice currency-based type interface. And in this case, we'll turn the metric off. You'll notice that the joins are all inner joins. Microsoft Tabular Models and Microsoft Multidimensional can only handle inner join type situations. And last but not least, we will add a quick hierarchy or set of hierarchies to our cube when it is built, 2 date ones and 1 product hierarchy, and that'll be a regular product hierarchy. With the process button, and execute the model from Pyramid, which will actually mash up the data and then go ahead and publish a new tabular model directly to the server. And now it's ready for some kind of analysis right on the fly. Here we can see we're going to look at 2 different dimensions and simply look at it by sales figures to get the general sense, and then margin, and finally cost. And you can see all the numbers flowing through and all the metrics working as you would expect. And you've got full-blown slice dice capability in Pyramid, natively querying the Microsoft Tabular Model natively and directly. In fact, if a user didn't want to start with a model but began with an existing Microsoft Tabular Model, in this case the one we just created, they can simply open it and use it. So not everybody has to create a model. More often than not, you just want to use one. This is the same model now being used through the Smart Discovery tools, which is an automated system for building visualizations in the most optimal fashion based on users' data selections from the model. And in the last example here, we'll run a natural language query against the exact same data model on the tabular server. Pyramid's NLQ engine is capable of running all kinds of queries against all kinds of supported technologies, not just the proprietary inbuilt one. And we'll do a quick extension of that by showing sales and margin by manufacturer, and we will add to that promotion category as well. In the next example, we're going to show how Pyramid can expose the full power of the MDX querying language against both Microsoft multidimensional and tabular cubes and models. To demonstrate, we're going to do a simple calculation of sales divided by quantity, and we will show the resulting query here. That execution on that query is actually run on the server of the tabular engine, but is designed and constructed from inside Pyramid. And you can see we can slice, dice, drill down the queries using that metric, even though it is not designed and executed on the server itself. Sorry, designed on the server, but executed from the client. And this obviously includes the ability to do things like totaling and whatnot. The calculations are not just across the measures. A key differential in pyramid is we're able to create calculations on members. And in this case here, we're going to grab all the volume discount elements from the promotions and aggregate them into a single entity. And you can see that our sales by quantity metric, which is broken out by product on the top, also works with the new aggregated value. And this, of course, will fly through even to all visualizations and whatnot. Another important aspect to realize is all of Pyramid's analytical capabilities, which includes all the advanced visualizations, drop zone mechanics, calculations, whatnot, which work on any SQL database, equally work well on analysis services. Without going into great detail, one of the great strengths of Pyramid is being able to handle all the complex hierarchical queries that come from Microsoft cubes. Here we're looking at an accounting cube, which has got a parent-child hierarchy that is ragged, which means it's not even. And you can see as you look down the levels there, they're not equivalent numbers of levels per parent structure. And if we flip this to the accounting grid, we can see that cleaner as well. In the last instance, we want to show some of the more advanced calculation capabilities that are exposed by Pyramid through the MDX framework, which is fairly unique in the marketplace. Let's say, for example, I wanted to look at all sales numbers per element in the customer hierarchy as a percentage of its parent. Using the formula tool that you're seeing here, I'm going to say, please take the current element, which is whatever the element is at the time, from the customer dimension, from the geography dimension, and divide it not by itself but actually by its parent. So it's me divided by my parent, and I'm going to show that as a percentage. A pretty simple concept but extremely difficult to design in most tools, and it's point and click in Pyramid. So we're calling this percentage sales of parent. If we go back to the Discover interface and add percentage sales to this query, you should be able to see now that that metric is working throughout this query, and it works flawlessly. It doesn't matter how much I drill up or drill down in the interface, because it always is an immutable calculation. Again, designed in Pyramid, executed on the server. Tasmania at 53 is 1.6% of Australia 3.2, and Australia 3.2 is 3.11% of all zip codes, or which is in this case all geographic locations of 102. In fact, removing the sales figures from here, you can see how we can do this if I open up the United States and keep drilling down into the levels here. As I go down, it gets more and more accurate. Another kind of calculation that Pyramid is able to execute is lists or sets. We're able to formulate very complex set designs, again with our formulation tools. Here we're going to look at all counties, and from those counties I want to look at, say, the top 25 counties. And the metric I'm going to use to design that is none other than the calculation we designed in Pyramid itself, percentage sales of parent. And then from there, we might want to say, let's take the last, 15 items from the top 25 and finally sort that using labels in a descending order manner. Being able to design complex lists like this allow us to design far more powerful analytical environments, and ironically enough, keep it simpler for users who want to get to these kinds of calculations but really don't know how. So someone can actually formulate it for them, and then it just calculates it there. You can see here we're looking at that listing of counties with our percentage sales of parent broken out by sales team across the columns.